Physics students, good afternoon. Mr. Fuga here. In our video today, we're going to be looking at group problem number 6A, which deals with some of the ideas around energy and energy conservation. Specifically, we'll be looking at different forms of mechanical energy, so that deals with kinetic energy, gravitational potential energy, and spring potential energy. The problem that we are going to be looking at is available on Canvas. There's also a key on Canvas. If you're looking just for a copy of the problem or a key to the problem, you can reference those there. So as you'll notice, we don't have the problem directly pulled up here, and we have a little more space to work on the board. But what we've been looking at today is a scenario involving energy conservation. I'm going to go ahead and read us part of the background to give us some context of what we're going to do. You are at the state fair and want to win the coolest stuffed animal there to impress your date. Unfortunately, to do so, you must win the High Striker. It is the classic game of strength to slam a hammer onto a pedestal and send a ringer to a bell very high up. You've probably seen something like this before. You take what would be some type of hammer or mallet, hit it down on a pedestal, and that uses usually some type of spring to send a ringer up to a bell. If you hit the ringer up high enough, you win the game. So this game has you smash a spring-loaded button, which will transfer energy over to the ringer and send it up. The mass of the ringer you estimate to be about 200 grams, and the spring you smash you estimate to have a spring constant of 1,000 newtons per meter, which would be considered to be a pretty stiff spring. The bell hangs 4 meters above the ringer. To win the coolest stuffed animal, you must first figure out how much you need to compress the spring by hitting it with the hammer to get the ringer up to the bell. Find out if you can win this game. So as with many scenarios, one of the first and most helpful things we can do is get a bit of a picture going. Now, I'm going to keep this pretty simple, but in essence, we have a ringer, right? Some probably small metal device at the bottom of our game. And we're going to compress the spring down by hitting it with a hammer and sending that ringer up to a bell, right? That would be somewhere up here at the top. Right? To try to hit the bell, win the game. Now we're told a few things as it relates to the problem. We're told the mass of the ringer we estimate to be about 200 grams. I would go ahead, anytime you see a value in grams, go ahead and convert before you work with any equations. And I like to go ahead and just get rid of that value in grams. Just so all I'm looking at is our mass in the units that we'll need it to be. We're also told that the bell is about 4 meters above the ringer. That will be important as it relates to possibly solving for gravitational potential energy, or the energy of the ringer up near the bell. We're also told the spring that we're dealing with here as a spring constant that we estimate to be about 1,000 newtons per meter. So this is just a bit of a visual of what's going on with our game. Now, not a required part of what we're doing to draw a picture, but it does usually help give us some context. Now, there are several types of energy that we could look at here. We could possibly look directly at the spring and the energy or potential energy stored in the spring. That's a product of really the spring constant and how much we compress the spring. So our equation is 1/2 K multiplied by delta X squared to find the energy stored in the spring. We might look at the energy of the ringer as it moves off of the ground. That would be what we call gravitational potential energy due to an object's height. And this form of energy we can calculate. We know the mass of the object, the height of the object off of the ground, and gravitational acceleration. And then we also have an object that is going to be moving. In order to get it from the ground up to the bell, it has to move. And so we might need to look at kinetic energy, 1/2 mass velocity squared. So we've got a picture, and now we have an idea of what types of energy we could be dealing with and how we calculate for those. Now, the question, if you paid attention to what I was reading, says this. To win the stuffed animal, you must figure out how much you need to compress the spring by in order to get the ringer up to the bell. So we need to figure out really how hard we have to hit the spring. And we're going to measure that based on how much we compress the spring. Now, that means we want to end with finding a delta x value. That's really what we're trying to get to. How much do we need to compress the spring by? So how do we figure that out? Well, using the idea of conservation, right? And we've defined the word conservation to mean that the amount of what we start with equals what we end with. Now, as we will learn later, it's likely that oftentimes when we're dealing with things like energy, the energy with an object isn't perfectly conserved. Sometimes things like friction or air resistance or sound can take energy from an object that it doesn't necessarily give back. Here we're going to make an assumption that all the energy in our system is perfectly conserved with the spring and the ringer. And so, here's what that means. We can't necessarily start this problem by finding the energy that we store in the spring. We don't know delta x. But what we maybe could figure out is this. How much energy do we have at the top of the game when our ringer hits the bell? That's how much energy we need to give the ringer, and if we can find the energy we have to end with, we can work our way back to find the energy that we begin with. So, one thing that we can do is this. Let's look at the top of the game, right? Not when we compress the spring down, not when the ringer is moving up to the bell, but when the ringer is all the way at the top. At that point, our total energy would just be energy due to the object's height. And here's how we know that. The spring potential energy would go to 0 because once our ringer starts moving up off the ground, right, the spring has been released and it no longer is any energy stored in the spring. It's not being compressed at all, so there's no longer any energy stored there. We can also make the assumption that when the ringer gets all the way up to the bell, right, it's going to hit the bell and then begin to move back down. We're looking at the instant, the point in time in which our ringer hits the bell. And at that point, in order for the object to reach its height and then begin moving back down, it has to momentarily stop. The ringer is going to hit the bell, stop, and then begin moving back down. So at that point, our velocity would be 0, which means we have 0 kinetic energy. 1/2 mv squared would be 0. So all of our energy at this location is going to be energy stored due to the object's height. And we can find that. Gravitational potential energy, mass, gravitational acceleration, and height. Those are the variables that we need. Now, we're told in the problem we estimate the mass of the ringer to be about 0.2 kilograms. Gravitational acceleration for the Earth, 9.81 meters per second squared. And our height is 4 meters. So, we can find the total energy at the top, assuming that our ringer is stopped and that the spring has fully been released and transferred all of its energy to the ringer. So 0.2, 9.81 multiplied by 4, that gives us a value for our total energy, remember, of 7.85 joules. So now we have our total energy at 1 point. And if we make the assumption that our energy is perfectly conserved here, that means the energy we start with has to equal the energy we end with. So if we end with 7.85 joules, that's how much energy the ringer needs to hit the bell, win the game. Then that means we have to start with that same amount of energy, 7.85 joules. So back down at the bottom of the game, this is the point at which we are hitting the button to compress the spring and then shoot the ringer up. At this point, think about our total energy. We know the total has to be 7.85 joules, what we start with, we end with. But what forms of energy would we have here? Well, this is if we're saying that the bottom is when we hit the spring before the ringer begins to move, at that point, we will have some energy stored in the spring. Gravitational potential energy, well, our object has not begun to move off the spring. This is just the point in time when the spring is getting compressed. If we're on the ground, we can assume our gravitational potential energy is 0. And as well, if we're saying that the bottom of the game is before the ringer begins to move, this is just when the when the spring is compressed. our velocity would be 0, which means our kinetic energy would be 0. So initially, all the energy in our system gets stored in the spring then gets released. That energy converts to energy of motion, kinetic energy, as well as gravitational potential energy, energy due to an object's height. But this is just the point at which, hey, the spring is compressed. We have to give the spring a certain amount of energy so that that energy can be transferred to the ringer, and the ringer can do its job to move up and hit the bell. So we know our total energy has to be 7.85 joules. That is the amount of energy needed in order for the ringer to hit the bell. And that energy will initially be stored in the spring. 1/2 K multiplied by delta X squared. So at this point, we know our spring constant. It's really a matter of plugging our values in and solving for delta X. So 7.85 joules is equal to 1/2 multiplied by 1,000 newtons per meter multiplied by delta X squared. 1/2 times 1,000, I would go ahead and multiply those. That's going to give me a value of 500 multiplied by delta X squared. I can then divide both sides of my equation by 500. So 500 over 500, those values will cancel out. So go ahead and plug this in, 7.85 divided by 500. I get about 0.0157, but remember that's equal to delta X squared. So we have delta X squared is equal to 0.0157. I'll then take a square root of both sides of my equation. Delta X squared will just give me delta X. And 0.0157, sounds like a bell, 0.125. Now, you might notice that value seems pretty small. But remember, what is delta X? Delta X is the change in length of our spring, whether it's being extended out or compressed down. Here it would be compressed down. But remember, the standard unit for a distance or a length is going to be meters. Right? When we deal with things like springs, we're typically not going to be looking at things in the 1 meter range. We're usually looking at springs that are somewhere in the 10 to 30-ish range, sometimes even smaller than that. So I would probably want to convert this to centimeters so that I have a better idea of what's going on with the spring. Well, that would mean I would then, in order to win the game, I would need to compress the spring by 12.5 centimeters. If you do look at the group problem itself, we are told near the end that we estimate that with our hardest hit, we can compress the spring by about 15 centimeters. So if I'm able to compress it by 15 centimeters, but I only need to compress it by 12.5, that tells me we're good to go, right? I no longer have to worry about winning the game because I'm able to compress it by 15 centimeters, but I only need to compress it by 12.5. So hopefully this gives us an idea as to how to look at the energy in our system at different points, at the top and at the bottom, and using the ideas of conservation. Now, one of the last parts of group problem 6a, a bit of an extension, is looking at the velocity of the ringer at a distance of 1.5 meters off the ground. So coming back to our picture, that would be roughly about here, right? What would the velocity of the ringer be at this point? Technically, we can find the velocity anywhere, but this is the point in which we are asked to look at. So here's what we can do. At this point, I'll call it midway, even though technically midway would be halfway up. We'll just kind of put it in quotations. It's kind of midway. Not really midway, but we'll just kind of make that just a good way to describe what's going on here. Now, at this point, kind of partway or midway up, the total energy still needs to be conserved. If we're assuming that, hey, we're not losing any energy to air resistance or friction or sound or anything like that. So the total here still needs to be 7.85 joules. If we want to win the game, we have to make sure that we're not losing energy. Energy here is going to be converted from spring potential to gravitational potential to kinetic, but we're not gaining or losing energy here. Now at this point, we are some height off the ground, so part of our total energy is going to be energy due to the height of the object, and we are also going to be moving, so part of our energy is going to be kinetic. We can probably assume spring potential energy is 0, because once the spring is compressed and then released, it transfers all of that energy to the ringer. So we can pretty much assume spring potential energy, there wouldn't be any spring potential energy in this part of the problem. So now our total, we still know our total is 7.85 joules, but now that total is going to be broken up into two forms, gravitational potential and kinetic. Now gravitational potential energy, mgh, plus spring potential energy, kinetic energy, 1/2 mv squared. Now, in the context of this problem, I'm trying to find the gravitational potential, I'm trying to find the velocity. So in order to do that, I need to know some of these other things that are going on. I know the mass of my object, I know the height, so I can maybe find that chunk, how much of our energy at this point is gravitational potential energy. I'm going to do that over here. So our gravitational potential energy, if we are 1.5 meters off the ground, our mass here is 0.2 kilograms. Gravitational acceleration, 9.81 meters per second squared for the Earth. And our height is 1.5 meters. 1.5 here is just an arbitrary number. We can technically solve for these things at any point, as long as we know the mass of our object and the height. So 0.2 multiplied by 9.81 multiplied by 1.5, we get about 2.94 joules. Now again, hopefully that value we recognize is lower than our total, which it should be. Again, this is not the total energy in our system. This is just how much energy is considered gravitational potential energy. So now I'll bring that value back. I know the total amount of energy, 7.85 joules. I now know how much of that energy is gravitational potential energy, 2.94 joules, plus 1/2 mv squared. Now I can subtract over the amount of energy that we solved for a moment ago. That was gravitational potential, 2.94 joules. So 7.85, subtract 2.94, I get a value of 4.91. So, conceptually what that means is that 4.91 joules of our total energy here is equal to 1/2 mv squared, which means this is how much energy is considered kinetic energy. Right? Here, and conceptually, a bit of a side note, more of our energy here is kinetic because we're not at the midway point. Right? When the spring is released and it converts its energy directly to the ringer begins moving and it's launched out at its fastest velocity. So at that point, just when our ringer gets launched, almost all of the energy in that system is going to be kinetic energy. And as the object begins to move, it tends to slow down, which means our kinetic energy goes down because our height is going up, right? Our gravitational potential energy increases as our kinetic energy decreases. So we should have more kinetic energy here than gravitational potential because we are less than halfway up our game, if you will. So now I can plug in the value I know for the mass. So 4.91 joules of energy is equal to 1/2. Our mass was 0.2 kilograms. Multiplied by v squared. I'm going to go ahead and write this as 1/2 times 0.2. Just going to divide that number in half, so that would be 0.1. So this would be something like 0.1 times v squared. I can then divide both sides by 0.1. So 4.91 divided by 0.1 gives me a value, so it'll cancel out. V squared equals 49.1, right? V squared is by itself now because the 0.1s have canceled out. And then now lastly, we'll take a square root of 49.1. You might recognize 49.1, pretty close to 49, and 49 is a perfect square, so we should get something right around 7. When we plug this value in, we do get about 7.01. And as with any time we take a square root, technically we have two answers. Positive and negative 7.01. Since our object is moving up, if we really wanted to present the proper answer, that would be about 7.01 positive because of the direction. So this would be a way for us to find the velocity at 1.5 meters off the ground. Technically, we could find the velocity at any point we wanted, as long as we choose a height, right? And we can probably assume that as that height goes up, our velocity is going to go down because of what's happening with the energies involved. So hopefully this gives us a good idea of what we're doing in group problem 6A, using our ideas and concepts related to energy and energy conservation. As always, if you have questions, feel free to watch the video again.